Text categorization using sentimental analysis is a method of categorizing text based on words that may convey a certain positive or negative feeling. More companies are taking interest in this because it allows them to take huge sets of data and automatically extract the overall sentiment towards that object. This reduces the tedious task of having a human manually read all the data and then categorize it. Text categorization using sentiment analysis has been used in a wide variety of different applications, including product reviews, email categorization, movie reviews, and even to track online sentiment of politicians. Some of the common issues in sentiment analysis are problems also associated with the difficult task of natural language processing. And for our project, we hope to diminish these issues. Primarily, it is difficult to determine fact from opinion. A common example of this is in movie reviews, where a reviewer might write some sentences summarizing the movie plot in addition to his opinion about the movie. To tell if the movie is good or bad, a human can distinguish objective fact and subjective opinion, but it is much harder to create a model that can tell which part is plot and which part is opinion. Another issue is determining the sentiment in text with oddities such as sarcasm or improper grammar. For example, a product review for a bad vacuum might say, "This is the best way to not clean your house." Overall, this is a negative sentiment, but the use of a positive word might indicate the opposite. Depending on the chosen algorithm, this could easily confuse the system. For our project, we will be combining algorithms to solve both of these issues. We will first determine the subjective and objective statements through looking at the frequency of adjectives and adverbs in a sentence. The higher the frequency of these parts of speech, the greater the probability that it is a subjective statement. To find the part of speech of a word, Apache OpenNLP, an open source Java library, can be used. In order to overcome speech oddities such as sarcasm or poor grammar, we will be employing the naive Bayes algorithm to classify text. Naive Bayes is notable for not correlating data, but rather looking at independent features. Therefore, speech oddities can be mitigated. In text classification, naive Bayes uses word frequencies, also known as the bag of words model, in order to classify a text. Naive Bayes takes into consideration the probability of a positive-negative review, as well as the probability that the words in the review correlate to a positive-negative review. In order to train the naive Bayes model, we will have to manually go through reviews and mark positive or negative sentiment. Our project will consist of creating a Java program which will first train our naive Bayes model on a set of data. After training, a product review can be inputted. This product review will split subjective and objective statements. Then, using the naive Bayes algorithm, the sentiment of each of the subjective statements will be determined. Finally, the average of these sentiments will be taken to determine if the review is positive or negative. The first step in our method to sentiment analysis is to apply the Apache OpenNLP open source Java library to a block of text. OpenNLP is designed to efficiently process natural language text. It includes many useful features that are central to language processing, particularly methods and parts of speech tagging, to classify adverbs, nouns, etc. We have written a Java program to do this. This Java program identifies parts of speech and labels them, and then isolates and displays only the adjectives and adverbs. Using a sample review, we are going to apply the POS model functions to classify the words in the review. The classifications are specified by the tags used in the Penn Tree Bank project. Running the excerpt through the program POS detector yields the following output. We want to capture the frequency of adverbs and adjectives because they represent the descriptors of the writer. With the parts of speech properly tagged, it is easy to separate these elements from the rest of the text by looking for JJ and RB tags. The POS detector program outputs this data also, after outputting the tagged text. Based on the same review, the program found 12 adverbs and adjectives. The output reveals a major issue with using just the subjective terms by themselves to determine the positivity or negativity of the reviewer. Based on the collected terms alone, you might think it is a positive review, yielding such adjectives as good and successful. However, the review as a whole was clearly negative, and besides those few adjectives that suggest a positive review, the rest of the terms are rather neutral. Consequently, we need another system to detect sarcasm and find other words that could correlate to a positive or negative review. To do this, we will implement a naive Bayes algorithm. These algorithms, when trained with test files, generate strong independence assumptions between the features. Naive Bayes is a widely used baseline for judging documents and classifying text. A common example of its practical usage is separating spam from legitimate emails. A public domain repository by Datumbox that offers its own API for machine learning tools uses the naive Bayes model to differentiate text in different languages by training it with tests in English, French, and German. We will be using this in the future to determine and classify the sentiment of our input. For our project, we will have two naive Bayes models.
I'm going to explain how our naive Bayes filters work, and I'm going to use our negative and positive sentiment analysis one, and then I'll quickly talk about how this differs from our subjective and objective ones. So we have both naive Bayes class, and then we also have the naive Bayes model. So the naive Bayes model is the entire model. So this includes both the positive and negative directory. And so we create classes for both of those, and then we train them. And how we train them is we go through the files. So it takes in a file path, and then it goes through each child in that directory. And then it parses the text so that it can go through. And then for each word, it will add it to our hash map, which contains the word frequency. And so it goes through all the files, and it does this through the bag of words method. And then we count the total words. So we create the vocab for both the positive and the negative from our test data, or from our training data. So then we combine the vocab, so we have an entire set of vocab between the positive and negative directories. We calculate the probability of our classes here. And then we create a file where our results will be written to. So then we go through our test data now, and then we go through our test data, we parse it out, we go through each word within the test data, and then calculate the probability of it being in the positive class and then the negative class. And then we collect all of those probabilities, we sum them up, and then we use the probability of that class occurring, and we take that, and then based on whichever probability is greater, we classify it as being positive or negative. And we do that for each file, and then down here we count both the positive and the negative total. And then for our subjective and objective, we do a very similar thing, except now we parse it off just by sentences. And so we classify and we train based on sentences instead of entire document. So here I'll be demonstrating how we run our program. So you go to Java, we'll look at our run configurations, which outlines our arguments, including all the places where our files are. So we're taking training data from here for our positive, naive Bayes, our negative naive Bayes, subjective and objective, and then this is our training data. So we hit run, and it tells us that we're classifying files in source/test data _ Cornell version 2 positive. So this is where our data set is coming from that we're classifying. And then currently it's running classifying for just positive and negative, and so we'll see those results soon. So our results were that we classified 137 files as being negative and 864 as being positive. So now we're running our positive and negative classifier with the objective filtering on top, and so we'll see that results shortly. So we classified 145 as being negative in this case, with 856 as being positive. So finally we say that we see our results in this test folder. So when we go to that test folder, which is here, we have where we took our test data from, which is this positive file here. We've also created this positive filtering file, which includes all the data that's been filtered. If you go here and go to the bottom, you'll see a file that contains all of the results. So how we produce our results is, as you can see here, we take in the files that have been given, which is our positive training directory, negative training directory, and the training directories for our subjective and objective, as well as the final test directory. So we go here and we first run our naive Bayes filters using our subjective and objective ones. So this one essentially creates a new directory that's the same as the test directory that you passed in. However, it excludes all of the objective sentences. So it only includes the subjective sentences for each one. So we take that directory here, and then we run our filter with just the positive and negative classifying results, and then we run it, which is right here, and then we run it with just with the positive and negative classifying results, but now we use it on the directory that just has the subjective sentences. So we're comparing here the difference between the naive Bayes filters with just positive and negative, and then the naive Bayes filters with positive and negative, but with objective filtering on top of that. And so if you look at our results, with the objective and subjective filtering, there wasn't much of a difference adding that on. So as you can see here, overall with this data set, without the objectivity filter, so just with positive and negative, we're at 81%. With the objective filter, though, we're only at 80%. So there's a slight decrease there. With our other data set, we actually see a slight increase from 78% to 79% with the objectivity filter. So what we found out through this project is that our positive and negative naive Bayes filter is very effective on its own. So adding the objective filtering on top of that doesn't change how effective it is, because sentences that are objective will have words that have a pretty neutral probability between positive and negative. So they're not affecting the result much to begin with, so taking them out won't really affect the result any further. So we've proven that just with a negative and positive naive Bayes filter is quite effective, and adding a subjective and objective filtering on top of it won't really affect performance, and for the worse or for the better.